In today's video, we'll be introducing an idea that you'll carry with you through every science class, and that is the concept of units. In the context of science, a unit is used to quantify a measured value and make it easier to relate measurements of different things. All measurements contain two parts: the number, or the quantity, and a scale, the unit. In order to properly compare measurements, there needs to be a standardized system of units. The most widespread system is the International System of Units, or SI. The SI base units that we'll be dealing with for now are meters for length, seconds for time, and kilograms for mass. Along with the base units, there are also metric prefixes that we use to express very large or very small measurements. For example, say you measure the length of something to be 0.0002 meters. Writing it this way can be a little cumbersome and hard to read. For this reason, we have a system of standardized metric prefixes as well. Here are all of the important metric prefixes. These simply get added onto the name of the base unit. For example, 10 to the 3 meters, or 1,000 meters, is equal to 1 kilometer. This also works for very small measurements too, because something like 0.02 meters is just 2/100ths of a meter. A centimeter is 1/100th of a meter, so this is equal to 2 centimeters. In addition to the base units, there are also some units that are derived from them. The one we'll be using today is the liter for volume. And it's derived like this. Suppose you have a cube that is 1 centimeter on each edge. 1 centimeter. So the dimensions of this cube or box is 1 centimeter by 1 centimeter by 1 centimeter. And we can multiply units just as we would numbers. So the volume of this box, length times width times height, we call that 1 centimeter cubed, or cubic centimeter. And the liter was created by saying that 1 cubic centimeter, the volume of this box, is a milliliter. And using our prefixes from before, we know that this is 1/1000th of a liter. One thing we have to account for when taking measurements is uncertainty. Here's an example. Suppose we have a beaker that's partially filled with water. We can see that the water reaches about halfway between 30 and 35 milliliters, but it's not exactly on a line. We can estimate and say that there's 32.5 milliliters of water in here, but there's no way to know for sure. You'll see now that every measurement we take has some degree of uncertainty. Now let's talk about how to quantify a measurement's uncertainty. As you can see, this reading from a digital scale gives the mass of this object as 10.0961 grams. Now, notice how this scale rounds off the measurement to 4 decimal places. So what we cannot do is assume that the mass of this object is also equal to something like 10.09610000, so on, grams. And you'll see why in a moment. Even though these numbers are numerically equivalent, they are not the same thing in the context of a measurement. For this measurement, we can only be certain about these first 4 decimal places, because those are the only places that the scale measures up to. So the mass of this object could really be anywhere in a range around 10.0961 grams. So we can't assume that it's exactly equal. Therefore, these 6 digits are the only certain digits of this measurement. And for that reason, we call them significant digits, or significant figures, sig figs for short. It's very important to account for sig figs calculations, so we need to first know how to count how many sig figs are in a given measurement. The first rule is that any non-zero digit is always significant. For any zeros in a value, there are 3 special cases. The first is that leading zeros, or zeros at the very beginning before any non-zero digits, do not count as significant. Because, for example, if we had something like 36 feet, writing 36 feet doesn't change anything about the accuracy. Next, captive zeros, or zeros between non-zero digits, always count as significant. For example, if we have 1.008 millimeters, this number would have 4 significant figures in total because these zeros do count. Lastly, trailing zeros, or zeros at the very end of the number, only count if the number has a decimal point. For example, if we have something like 0.25 centimeters and 0.250 centimeters, as I discussed earlier, this second measurement is more precise because it measures 3 decimal places. Therefore, we say that any trailing decimal zeros, if we were to add even more, that just increases and increases the accuracy of our measurement. So those are significant. The last rule regarding sig figs is that exact values, or values that are counted and not measured, like if you're counting the number of apples or oranges, do not affect sig figs in a calculation. For me, the best way to memorize the sig fig rules, especially those zeros, is to just practice. So let's do it for you. Example 1. Say a student measures out 0.0105 grams of caffeine. How many sig figs are in this measurement? We know from our rules that leading zeros at the beginning, before the first non-zero digit, do not count significant. So these are not counted. Now we have this string here at the end. We have a non-zero digit and a non-zero digit at the end with a 0 in between. Our rule said that captive zeros are always significant, so all 3 of these digits count significant. So there are a total of 3 sig figs in this measurement. Now, what if we were to add a 0 to the end here? If, for example, the student used a more precise scale and it gave you this. Well, we're adding another decimal place. So this trailing 0 is significant because it's a decimal. So this measurement has 4 sig figs. For calculations involving 2 different measurements, the one with the least number of sig figs is called the limiting value, or limiting term. For example, let's say we're calculating the density of an object, which is mass divided by volume. Say we're examining a liquid, and we take its mass to be 19.625 grams. We have all 5 non-zero digits here, so it's pretty easy to determine that this measurement has 5 sig figs. And let's say that the volume of our liquid was measured to be 25.01 milliliters. We have 2 non-zero digits at the beginning, so these are of course significant, and we have a captive 0 with a non-zero digit at the end, so that counts as well. So this measurement has 4 sig figs. When we calculate the density, 19.625 grams divided by 25.01 ml, plugging this into a calculator, we get 0.78468612, and it keeps going. In a lab report or any formal assignment, we cannot report this exact long decimal, because doing so would assume that these 2 measurements are perfectly accurate, and that, for example, we could keep adding zeros to them. But of course, no instrument of measurement is perfectly accurate, and therefore these measurements are only as accurate as the amount of significant figures they have. So the one with the least number of sig figs will limit the accuracy that we are able to report with certainty in our final answer. So for this case, we have to round our final answer to just 4 sig figs. So when we round it, we get 0.7847, because this 8 rounds the 6 up to a 7. And this is 4 sig figs because the leading 0 is not significant. And for our unit, we can multiply and divide units just like you would a number, as I showed earlier. So our unit would be grams divided by milliliters, or grams per milliliter. And that's the density of this liquid. Now let's talk about how to convert between different units. In the top right, I wrote down some unit factors that you may already be familiar with, but let's examine how we can use them to our advantage. Say we're given an arbitrary measurement like 13.52 inches. How would we convert this to centimeters? We want to multiply this by 2.54 centimeters over 1 inch, and you'll see why in a second. Just ignoring the units for now, when we do this multiplication, 13.52 times 2.54 over 1, so just 2.54, we get 34.34. Now for the unit of our final answer, we have an inch being divided, since it's in the bottom, by another inch. So these two cancel out, and we're left with centimeters. So that's how you would convert inches to centimeters. We put our target unit on top. And the reason why multiplying by this unit factor works is because it's really the same thing as multiplying by 1. As this unit factor up here conveys, 1 inch is equal to 2.54 centimeters. So multiplying by 2.54 centimeters over 1 inch, since they're really the same amount in terms of distance, it's really the same as multiplying by 1. And when you do the multiplication, the units cancel and it converts the unit. Let's try another example. Say we want to convert 58 kilograms to pounds. Let's try another. Say we want to convert 58 pounds to kilograms. Let's use our unit factor again. This time, we have to have 1 kilogram on top since it's our target unit, and pounds on the bottom to cancel it out. And when we plug this in, 58 times 1 over 2.2, so really 58 divided by 2.2, is equal to 26, rounded to 2 sig figs, and our unit would be kilograms.